Hi, welcome back. This is Professor Ridge, and today's lesson on 9.7, Applications of Exponential and Logarithmic Functions. Okay, so let's look at exercise 4. So we'll just do we'll do like 3 or 4 of these examples. Alternative fuels. The number of gallons of ethanol produced in the United States can be estimated by this function. E of t equals 0.18 times 1.137 to the t, where E of t is the annual production in billions of gallons and t is years after 1980. So t equals 0. T equals 0 is 1980. So t equals 1 is 1981. T equals 10 would be 1990. So on. Okay? So let's see. A, what year did the U.S. produce 5 billion? So let me translate this. It says solve for t when E of t equals 5 billion. So we're going to put 5 in for E of t. 1.137 to the t. So this is an exponential equation. Let's get the exponential part, this part, by itself. So you got to divide by the 0.18 on both sides. So 5 divided by 0.18. $27. Okay, so we'll just leave that as that number. So 1.137. It's better not to round until the very end. So we'll just leave that number like that. It's 27.7777. So we'll just leave it. Now we're going to take ln of both sides. And remember, we're going to bring the t out in front. So I'm going to kind of skip a step there. So it's ln of 1.137 t, and then the 7 by the power rule for logarithms, the t comes out in front. Okay, and then I'm going to divide. Remember, this is just a number. So I'm going to divide both sides by that ln. So I got ln 5 over 0.18, and I'm going to divide that by ln of 1.137. That equals t. Now that's my exact answer. Punch it into my calculator. T is about Okay, so when we do this, I want to make sure I use parentheses. So it's ln parentheses 5 divided by 0.18 parentheses. Equals 3.324. Again, make sure you know how to use your calculator. And then I'm going to divide that by ln of 1.137. So that's about 25.89. 25.89. And we probably want to round this to the nearest year. So 26. So the time, remember, t equals 25. That's going to give me what year? So the year is, we'll say 26 years. 1980 plus 26. So that's 2006. Okay. All right, for B, what year was the U.S.? Okay, so same thing. We want to solve for t, but we're going to have 25. Okay, we're going to follow the same steps. We're going to divide by 0.18. So those cancel. And then we're going to take ln of both sides. Bring that t out in front. I kind of skipped a step there, but I'm just kind of looking above at 8. I kind of already know what the answer is going to be. So again, I don't punch anything into my calculator until the very end here. Punch all that in my calculator, so T is going to be about, let's see, ln of parenthesis 25 divided by 0.18. Now if your calculator is typed where you got to put in the numbers first, then hit the ln button, do the 25 divided by 0.18, hit equals, then the ln button, hit equals again, which that should give you 4.9333. Leave that in your calculator, then divide it by, then put in the number 1.137, hit ln, then hit equals. Okay, if you have the type that, like the one I'm using, you hit ln parenthesis 25 divided by 0.18, close parenthesis, hit equals, and then divided by ln. Actually, you don't need to hit the equals. You can just punch it all in. 1.137. As long as you use the parentheses, we'll be okay. And that's 38.42. So that's going to give me the year, so let's say 39 plus, see, because we're into the next year, so we're going to go to 39. So that would be, well, actually the book's just rounding it off, so they're saying about 2018. I actually would say you're into the 2019, but we'll just stick with what the book says. Alright, so 2018. Let's try another one. Alright, so before we do the next problem, let's write down the exponential growth model, which is P of t equals P sub 0, or P naught, times e to the kt, and k has to be positive for it to be growth. Now, I'm going to write down the decay model in a minute, and that's just k would be negative. So, again, this is the exponential growth model. Now, if we're talking about populations, P sub 0 stands for population at time 0, P naught, population times 0. P of t is the actual population at a given time, t. K is the exponential growth rate. So if population is growing at a rate of 5% per year, that would be 0.05. And then doubling time, that's a common question, is how long does it take for the population to double? And that's called the doubling time. Okay, that's the time necessary for the population to double in size. All right, now this growth model can be used for anything, not just a population. It's, you know, you can think of it as an amount too. So whatever's doubling or growing. So typically we call that a population, and it could be population for people, the number of bacteria, whatever. Alright, so let's try one of these. Okay, so let's look at 24. It says in 2008 the world population was 6.7 billion and the exponential growth rate was 1.14% per year. We want to A, find the exponential growth function, B, predict the world population in 2014, and C, when will the world population be 8 billion. So we start out with just the general exponential growth model. So we know that in 2008 population was, so t equals 0 is, or 2008. So t equals 1 is 2009, t equals 2 is 2010. Okay, so we're gonna say at time 0 our population was 6.7 billion. Oops, put that in the wrong spot. Oh yeah, no, that's the right spot. 6.7. equals 6.7 e to the k. Oh, I'm not trying to figure that out. Sorry. Let me get my head straight here. Okay, so P of t is equal to 6.7 e to the k, which is the growth rate, which is 0.0114 t. So this is the growth model. B, predict what the world population will be in 2014. So if it's 2014, so that's 6 years. So t equals 6 is 2014. So we're asking what's P of 6. So 6.7 e to the 0.0114 times 6. So we just punch that in our calculator. So that's going to be equal to, so I'm going to do this, you got to use parentheses around that. So we're going to go, again, it just depends on your calculator which way to punch it in. So 6.7, this is the one I'm using today. I can just punch it in the way it reads, but I have to use those parentheses. So 6.7 times e to the parenthesis 0.0114 times 6 close parentheses equals, and I get 7.17. So that looks like 7.2 billion if I round it. That's, the book rounded it to that one decimal place there. So about 7.2 billion. And then for C, when will the world population be 8 billion? So we want to find T when the population is 8 billion. Okay, so we're going to divide both sides by 6.7. Remember, we got to get the exponential by itself, just like we did before. We're just going to leave that there. We're going to take ln of both sides. So I'm going to take ln of both sides. The L and E cancel each other, so I get 0.0114t, which makes it nice. And then I'm going to divide by the 0.0114 on both sides. So t equals ln of 8.0 divided by 6.7 divided by 0.0114. So t is about, punch that in my calculator. So let's see. So again, make sure you know your calculator. So ln 8 divided by, oh, I don't know my calculator, parentheses, 8 divided by 6.7 equals, I got 0.177, then divided by 0.0114 equals 15.5. So we'll round that to 16. So that's about 16, and that's year, let's see, 2008 plus 16, 2024. So it's about year 2024. All right. Let's try another one. Next page. Okay, so wind power. U.S. wind power capacity has grown exponentially from about 2,000 megawatts in 1990 to 17,000 megawatts in 2007. A. Find the exponential growth rate K and write an equation for an exponential function that can be used to predict U.S. wind power capacity T years after 1990. And B, estimate the year in which wind power capacity will reach 50,000 megawatts. So basically what we're going to do is think of this as 2 points, and we're going to write our general function, growth function, and we know P sub 0 is 1990 is the 2000, so remember, so T equals 0 is 1990, and we have that point. We have, if T is 0, the output is 2000, or the capacity is 2000. And then we got another point, if T is 17, it looks like. So 1990, let me just make sure I wrote these numbers right. Yeah, so that's 17 years, is 17,000. Okay, so we're going to use this first point gives us this formula, P of T is equal to 2000 E to the KT, but we don't know what E is. So P sub 0 is the 2000. Now we're going to use the second point. Remember, this is P of T, and this is T. So we're going to put in 17,000, 2000, E to the K times 17. We're going to solve it for K. So we've got to get the exponential by itself. So divide both sides by 2000. So we get 17 over 2 equals E to the, I'll just rewrite it, 17K. Take ln on both sides. So 17 over 2. ln and E cancel each other, so we can just get 17K. And then you're going to divide both sides by 17. So K equals ln of 17 over 2 divided by 17. And if you can store that number in your calculator, that's even better. It'll get you more accurate answers. So if I do ln of parentheses 17 divided by 2, close parentheses, that equals 2.140066163 divided by 17, and that's 0.12588.624. Okay, so it depends on how far out you want to write this. Let me look at something here. How far out did they go? They just went 3 places. 0.126. Okay, but if you want a little more accurate, you want to go out more places. And better yet, if you can store that in memory and then just have it that way. Alright, so that was A. And then, also we want to write the function now. P of T is equal to 2000 E to the 0.126 T. So that's A. B. Now we want to figure out what year it will be 50,000. So find T when P of T equals 50,000. So we're going to do 50,000 equals 2000 E to the 0.126 T. Divide both sides by 2000. So remember, you always want to get that exponential by itself. So 50 divided by 2 is 25. Now it's pretty simple from here. You take ln on both sides, and what's nice about this one, if it's base E, the ln and E cancel each other, so you get 0.126 T. Now divide both sides by 0.126. And again, better yet, if you left that 0.1258886, whatever, in your calculator, you can use it or put it in memory. But we'll just round it like this. So ln 25 equals 3.21. I leave that in my calculator, divided by 0.126 equals 25.546, but we're just going to round it. We'll round it to one place, 25.5. And again, we want, what year would that be? So that'd be year, so let's see, we'll round that 26 years, 1990 plus 26 years. No carry. 11, 2016. Is that right? Oh, they got 2015. Why did they round it down? I don't know. Maybe they left the 0.12588 in the calculator. Let me try that. ln of 25 divided by 0.1258886. No, still 25.5. So anyway, so that'll be year 2016. Alright, let's try a decay problem now. Okay, so the exponential decay model is a function of the form. It's basically the same function, but when you're done, you're going to have a negative exponent up here. So k is positive, but if it's decaying, then you're going to put in a negative number. Okay, so if the decay rate's 5%, then you put in -5 up for k. Okay, so p sub 0, same thing, the original quantity times 0. P of t is the amount present at time t, and then k is the decay rate, and then half-life would be a common problem for decay problems. It's the amount of time it takes to get half of the original amount. So that would be the half-life, and we use that usually for carbon dating. So let's try a problem. Okay, so the decay rate of krypton 85 is 6.3% per year. What's its half-life? So we start out with our formula, P of t, decay model, P sub 0, e to the negative kt. So let's see, P of t would be P sub 0, e to the negative 0.063 t. Now to get a half-life, we want to find t when P of t is equal to a half P sub 0. So we're going to plug in P 1/2 P sub 0 equals P sub 0 e to the negative 0.063 t, and then you're going to divide both sides by P sub 0. So it doesn't really matter what you start out with. To get the half-life, you're always going to get 1/2 equals e to the negative 0.063 t. Pick ln of both sides. So the ln and e cancel each other. And then divide by the negative 0.063. And punch that in your calculator. So t is going to be about, so ln 1/2 is 0.5. ln 0.5 equals negative 0.693 divided by 0.063. So it's 11.00, so it's about 11 years. See how many, yep. So we'll round it. It's 11.002, so about 11 years. Okay, so pretty straightforward. Let's try another one. Okay, so 39. The half-life of caffeine in the human body for a healthy adult is approximately 5 hours. So what is the exponential decay rate? So for A, we got to start out with our exponential decay rate. So half-life, 1/2 P sub 0 equals P sub 0 e to the negative k times 5, because it's 5 hours. So our rate's going to be per hour when we figure out k. So again, you divide by p sub 0, they're going to go away. Then we're going to take ln on both sides. So I got ln of 0.5 equals negative 5k. And then you're going to divide both sides by 5. Or negative 5, sorry. So k equals, so k is about ln of 0.5 divided by negative 5. Which is negative, or no, it's positive 0.13886, so we'll round it. So it'll be about 13.9%. So that's my K. So B, how long will it take 95%? I'm going to do B up here so I don't have to use another piece of paper. So B, 439. How long will it take 95% of the caffeine consumed? So that we want 0.95 p sub 0 e to the negative 0.139 t. And we want to solve this for t. So again, I'm going to divide by p sub 0. So those cancel. So I got 0.95 equals e to the negative 0.139 t. Then we're going to divide by, or do ln on both sides. ln 0.95 equals negative, remember ln and e cancel each other, so negative 0.139 t. Now divide by the negative 0.139. So t is about ln of 0.95, which is negative 0.05, divided by negative 0.139. So it looks like 0.36 I did that wrong, didn't I? Hang on. Yes, we want 95% consumed to leave the body, right? So that means how much is going to be left is 5%. So this shouldn't be 0.95. This should be 0.05. That's why I'm getting a different answer. So we need a 05. 05. Alright, let's try that. So ln 0.05 equals, because remember 100% to start with, we're going to consume 95% or metabolize it, so we're left with 5%. So that's negative 2.999 divided by negative 0.139. So it's going to take 21.5 hours. Let me see if that one's right. Oh, I want to round it. 21.55, so 21.6 hours. And that's what the book says. So good. Alright, so that concludes the lesson for 9.7. Go to my math lab, complete your exercises there. And it looks like we only have one more section to do for the semester. Alright, see you next time.